Good morning. Let's get started. Welcome all to ICTS and to the 12th installation of the ICTS Summer Schools on Gravitational Astronomy. This is a series, as most of you know, has been running since 2013, and we have been focusing on different aspects of gravitational astronomy every year. And this year's focus is on continuous gravitational waves. And we will start with the course by Professor Dipankar Bhattacharya. Dipankar is one of the, perhaps the foremost astrophysicists of India, and he has made very impactful contributions in different aspects of astrophysics, in particular, study of compact objects, in particular neutron stars and pulsars. So it's a great pleasure to have him speaking on neutron stars, the astrophysics of neutron stars, as the first course. So without any further delay, let me invite Professor Bhattacharya for this first course.
Thank you so much. Am I audible? Okay. So,
one logistics remark. So if you have a question, I hope you are okay to
yeah, you can stop me anytime.
Yeah, it's preferable to use it on the mic because there is also a set of participants online. And for the online participants, you are muted by default, but you can raise your hand and one of us will unmute you so that you can ask your questions.
Thank you. All right, shall I start? Thanks for inviting me to give these lectures. And it's a pleasure to come back to ICTS. Actually, I came only before the pandemic, and it's been quite a few years since I've been here. So pleasure to come back. So good morning to you all. Let's begin. So we will start at the very basics regarding stellar equilibrium, structure of neutron stars, and then work our way up. So as we know, that stars are gravitationally bound configurations which are held against gravity by their internal pressure, right? So if we look at the stellar equilibrium equation, we will have, let's say, I take a spherically symmetric object, a star, and at a distance small r from the center, I can look for a parcel of matter. Let's say this cross section is unity and this distance is dr. Then in Newtonian gravity, we will just balance the forces on this particular piece of matter. The amount of mass contained within the sphere that is inside this radius r is m of r. Then I can just look at the gravity. It will be minus g m of r, and then mass of this little piece, which is rho of r times volume. Area is 1. Volume is dr divided by r squared. So that is the gravitational force on it. But then there is pressure, which is a function of r. So there is a outward pressure, which is P of r times area, which is 1. And there is an inward pressure, which is minus P of r plus dr. This is 0. So this is the stellar hydrostatic equilibrium. So you can and Taylor expand this and then rewrite this as minus dp dr is g m of r rho of r over r squared. And m of r, being the mass contained within r, is 0 to r 4 pi r squared. This can be written in a differential form, is dm of r dr is 4 pi r squared. So given these two equations, one can solve for the structure as long as we know a relationship between pressure and density. And this relation between pressure and density and possibly other parameters is one of the key issues in neutron star astrophysics, as well as many of the things that are being done even from gravitational waves. So we'll come to this in some more detail later. So this is, as is easy to see in Newtonian physics, an analog can be done in full GR, where you have to assume a certain symmetry. So in Schwarzschild metric, which is stationary non-rotating star, if you then take the hydrostatic equilibrium equation in Schwarzschild metric, then this equation in GR will look like minus dp dr is equal to g m of r plus 4 pi r cubed p of r rho of r plus p of r by c squared divided by r squared times 1 minus 2g m of r over c squared r. Okay. So this becomes a slightly more elaborate expression in full GR, and this is what we know as the Tolman Oppenheimer-Volkoff equation. Among astrophysical objects, it's mostly only the neutron stars for which we really need to consider full TOV equation. For all other objects, including compact objects like white dwarfs, just the Newtonian form of it suffices, because the radius of the object is much, much bigger than the Schwarzschild radius. So when radius becomes close to Schwarzschild radius, then the corrections become much more important. So when you're talking about neutron stars, this is vitally important. If you do this, you'll get a wildly different result. So you need to take into account the full GR. This expression remains the same. The mass within a radius r, that definition is exactly the same as in Newtonian context. So this equation also translates directly to the GR case, and then you have to supplement it by equation of state. Now the equation of state, if it can be written as pressure as a function only of density and no other parameter, it's we call it a barotropic equation of state. But if it has other parameters, for example, if it's a thermal equation of state, then you will have density and temperature, in which case you will have to have additional equations to determine how temperature also runs as a function of as a function of radius. In case of a regular star like the sun, that is indeed the case, and in order to define how temperature, or you have to derive how temperature depends on R, you have to then look at the radiation transport, the energy transport due to thermal conditions. So then you will have additional equations which you will have to solve along with to determine the additional parameters. In case of neutron stars and other compact stars, we really don't have to worry about it because the thermal component of the pressure is minuscule compared to the source of pressure that comes just being because the material being just very dense. So density is the prime factor which determines the equation of state. So therefore, we will not have to worry about parameters like temperature. But before we get to compact stars, there are a few things that we need to get an idea about. We want to understand some of the issues that we worry about in neutron stars. So I will start with this Newtonian equations, look at some basic properties and basic features of regular stars, and then transit onto compact objects. So let's consider a star that is supported by thermal pressure. Like the sun. Now, I'm not going to do a full elaborate solution of the stellar hydrostatic equilibrium equation because we're only looking at qualitative properties. We will look at just a very quick dimensional analysis of this equation. And then we'll be able to derive some dependencies. And that's what is important. So let's take this equation and do a drastic approximation. Left-hand side, I will write as, so this is dP dr. I will take central pressure as Pc. Surface pressure of a star is 0. So dP dr, I'll just do a linear approximation. 0 minus Pc over R. R is the radius of the star. So this is equal to, now I have G m, the full mass of the star, R squared, and for rho of R, let me just use the average density. So that is m by and I will not be worrying about this 4 pi by 3 because our drastic approximations are nowhere close to factors like this. So this will tell us that the central pressure of a star is roughly equal to G m squared over R to the power of 4, which I can also write as G m to the power of 2/3 rho to the power of 4/3. Rho is the density. In order to get a balance at the center, then we need to provide sufficient thermal pressure. And thermal equation of state is P equal to nkt as we know. So this is rho divided by mu mp. So this is, to convert the mass density to number density, we divide mass density by average mass per particle. K times T. So if these two have to balance each other, we can just equate these two, and then you will find that so this will tell you that rho to the power of 1/3 is kt over g mu mp m to the power of 2/3. Using this, if I use this in expression for PC, then we will have PC is g m to the power of 2/3, this to the power of 4. So you will see this is proportional to t to the power of 4 by m squared. This will also tell you that density, central density, is proportional to 1 by m squared, because in take cube on each side. Now let's take a look at what we have just done. Let's consider a diagram where I plot log of pressure versus log of density, and let's consider the mass to be of certain value. Then this quantity, the required central pressure, is some kind of line with the slope of 4/3 over here. Now, if I consider the central temperature of the star to be of a certain value, then given this, I have another line which is proportional to rho. So this star can find an equilibrium when these two cross each other. So at that point, you will have an equilibrium configuration of the star. An equilibrium doesn't mean it's a stable equilibrium. To see further, we need to take this equation and derive one more property of stars. So we have right? Let's multiply this by 4 pi r cubed and integrate over the whole configuration. This quantity, let me take it to the right hand side. I will take this negative quantity inside, minus, let's keep R over here. And so what is this quantity on the right? Any guesses? Gm rho over R times 4 pi R square dr integrated from 0 to capital R. Rho of R 4 pi R square dr is the mass of a small shell of thickness dr at radius R. Mass times the mass inside that radius times g divided by R. Exactly. So this is the integrand is the gravitational potential energy of this thin shell, and the integral integrates over the whole shell, whole star, all the shells. So therefore, this is the total gravitational energy of the star. What about the left hand side? I'll integrate by parts. So 4 pi R cubed P of R is my first term. I have to evaluate it to 0 and R. Then minus, I have 3 integral 4 pi R squared this I can then write as 4 pi R cubed P of R minus 3 pressure is related to the thermal energy density. And that relation is right, when gamma is the adiabatic index. If for monoatomic gas, gamma is 5/3, the P is 2/3 U. For radiation, gamma is 4/3, the P is 1/3 U. This you must have come across. So I can write this as 3 times gamma minus 1. Integral, let me not write it as U thermal, let's call it just U, internal energy, because it need not come just from thermal energy. So minus gamma minus 1 U this is internal energy per unit volume. So this whole quantity is the total internal energy. So I can then write this Eg plus 3 times gamma minus 1 U, capital U, so total internal energy is if I am looking into the full stellar configuration, where capital R is the surface of the star, then pressure at R is 0. So right hand side will be 0 for the full configuration. But you should realize that this is applicable to any part of the star. Even if I go not to the full capital R, but I take a small central region and I look at the quantity which is relevant to that region, this is still valid. And this is what is going to become important in a later discussion. But if you take the full star, you have P of R is equal to 0, and you have Eg plus 3 times gamma minus 1 U is equal to 0. Yes. But this is R cubed, no? So R is 0 at, so that goes out not because of, P is definitely not 0, it's maximum actually at the center, but R is 0. So this quantity for, let's say, hydrogen gas, gamma is 5/3. So this is 2/3 times 3 is 2. So for does this look familiar? This is a well-known theorem. So this is the virial theorem, right? And along with this, the full thing is called the stellar virial theorem. Let's look at the full configuration. We have Eg plus 2U is equal to 0. What is the total energy of the configuration? Right? So you see that this is minus Eg by 2. So this is an important indicator of how stellar configurations behave in and out of equilibrium. So assume that you have a stellar configuration which is in quasi-equilibrium with thermal pressure, has reached some equilibrium like that. It has a total energy content which is given by Eg plus U, which is equal to minus Eg by 2. But the star is hot and is embedded in empty space, so thermal energy must be radiated away. So if the thermal energy gets radiated away, then the total energy of the star drops with time. The total energy of the star drops with time And what happens to EG? Is it? Okay, sorry. U is minus 2. Yeah, you're right. I'm sorry. Because EG is already negative. All right. So, if E total decreases, what happens to EG? So, EG will decrease, but EG is a negative quantity, right? So, the magnitude of EG will increase. It will go more and more negative. Start with some negative value. E total is negative, of course, because it's a bound system. So, E total becomes more negative, EG becomes more negative. So, object becomes more bound, so it contracts. So, if you leave an equilibrium configuration, near equilibrium configuration like it, like this to its own devices, thermal energy will be radiated away and the object will contract with time. The total mass is not changing, so this white line actually represents the track along which a stellar configuration of a given mass is going to moves from lower density to higher density. The thermal energy, U, is minus Eg by 2, and it is positive. So as Eg becomes more negative, the thermal energy content is going to go up. So this is a paradox. You take thermal energy away and it gets hotter, right? Sometimes referred to as the negative specific heat of a gravitational system. So as thermal energy gets removed, the stellar configuration will keep moving up along this line and will continue to find a temporary balance with higher and higher temperatures. This is at a given temperature. At a higher temperature, you will have a line which goes above it. So from this temperature, if you move to that temperature, and go to higher density. You'll also notice that this is for a given mass, and this is proportional to m to the power of 2/3. So at a higher mass, I have to draw the line somewhere up. So for a given temperature, the equilibrium density is lower for higher mass stars. No, we are just taking here the central temperature, because we're only talking about PC, so the central temperature. If we have to take the whole run of temperature and density, we have to do the integration. So this very crude way of doing it does not capture that. So let's then try to reconstruct the journey of a gas cloud, which eventually becomes a star and then evolves and then forms compact objects. So first, it condenses at a low density, and then it moves because of its self-gravity and radiation being removed. Its gravitational energy rises. Half the amount of gravitational energy that is released in the process is radiated away. Other half goes to heating of the star. So its temperature increases and it condenses at the same time. And will continue to do that unless there is a process which can replenish the energy that is being lost. So at some point, since the central temperature is rising, the central temperature will become large enough for nuclear fusion to start. If nuclear fusion starts, let's say hydrogen now burns to helium, then as long as nuclear fusion is active, the fusion process will generate exactly the amount of energy as is being lost from the surface. So therefore, the total thermal energy of the star now remains constant. And equilibrium is still valid. If U is constant, Eg is constant. So the configuration stays as it is. It doesn't change in shape or size. So if this happens to be that temperature at which hydrogen burning will occur, then the star is contracting all the way gradually, and then it comes to this point, and it will stay stationary at this point as long as fusion is able to supplement or replenish the energy being lost from the surface. But as we know that amount of fuel is limited. Eventually, this fusion process will stop. Once the fusion process stops, it will just resume its journey as it was doing before. So what should happen next? Any guesses? You have to speak up, I can't hear you. It will further contract, correct? All right, so at some point the helium might start burning. So then as long as helium burns, again it will find a stable configuration for a while. That will also get consumed. After that, what? Okay, let's assume that happens, then what? Okay, so which nucleus is that? Okay, so now if you let this go, if there is nothing else intervening the process, then the nuclear burning will proceed all the way until the iron peak elements, iron, cobalt, nickel. And after that, it is no longer possible to generate energy. So it will, gravity will then win. But is it possible for all stars to go through these, all the nuclear burning stages? Does every star go through all the stages of nuclear burning forming up to iron? No. Is the sun going to do that? How far is the sun going to go? How many burning stages is the sun going to have? Will it burn carbon? it will have two stages, hydrogen and helium. After that, it will stop. You go to a little more massive star, it will go through one more stage. A little more massive, it will go through one more stage. Why is that? I mean, from this, it seems inevitable that as you keep contracting, you should be able to go through all the stages. So what is it that stops it from not proceeding beyond helium burning in case of the sun? If you take some even less massive star than the sun, they even will not proceed to helium burning, stop after hydrogen burning. And there are configurations which can't even get to hydrogen burning, like brown dwarfs. What is it that stops it from happening? What stops it from happening has a very fundamental role in everything related to compact stars. Okay? This is degeneracy. Let's look at the property of degenerate system. We will look at zero temperature gas made up of identical Fermi particles. So let's say electrons. Don't worry about anything else, just consider electrons as an electron gas. The charge of electrons which will lead to repulsion between them, we don't worry about that because there will be in the mixture sufficient number of positive charges, so the long-range interactions are going to be screened out. So just the fact that they are Fermi particles causes, even at zero temperature, their momentum to be finite. And this is a very basic property of fermion gas. So let's consider zero temperature, and I will look at the phase space volume. But it's a homogeneous system, so there is nothing which depends on space. So I'll just take an unit volume, that any unit volume is representative of any other unit volume. Let's say there are small n number of particles in unit volume. Okay? So the phase space volume of that is occupied by these particles is the unit volume in configuration space times the corresponding volume in momentum space. We will compute the momentum state volume, multiply by 1, so that will be our total phase space volume. What's the property of these fermionic particles? Is that if you have a state, you can put at most 2 particles with opposite spins in that state. If that state is occupied, the next particle can only go to the next higher possible state. Right? So basically that is the principle that will decide what is the momentum that the particles are going to have. So in the momentum space, let's consider some momentum P. I draw a sphere. Of radius P in momentum space. And I can count how many states are there within this sphere. That is, I take the total phase space volume described by the sphere. That is 4 pi by 3 p cubed is the momentum space volume times 1 is the configuration space volume. That's the phase space volume. In quantum statistics, the volume occupied by one state is h cubed. This is the number of states. And I can put up to 2 electrons in each state. So within a momentum p, this is the total number of vacancies available for electrons to occupy, or for any Fermi particle to occupy. Electrons need not be electrons, it could be any other Fermi particle. Now at 0 temperature, I will have to start populating from the lowest momentum and then go up. So if I count now the fact that there are small n number of particles which occupy this volume, and I count the entire phase space volume that is required to accommodate this small n number of particles, then I will have 8 pi by 3 p cubed by h cubed is equal to small n. So since this p is that special p which now exactly accommodates all the n particles, I will give it a special name. It's called Fermi momentum. So Pf then will be 3 by 8 pi, the power of 1/3, h n to the power of 1/3. Right? 0 temperature, no thermal agitation, but the momenta are not 0. So since particles carry momentum, they will also have pressure. They have a finite internal energy and they have a finite pressure. So how do I evaluate pressure for a distribution like that? Basic thermal physics tells us that pressure is nothing but flux of momentum. You take an unit area, you can ask what is the amount of momentum crossing that unit area per unit time. And since this is a three-dimensional thing, so we will have pressure is 1/3 average value of number times velocity times p. So n times v is the number of, is the flux of particles, each particle carrying momentum p. And since the p goes from 0 to pf, we have to take an average. So integrate this from vp, integrate from 0 to pf, and divide by the number of particles. So so this gives you the pressure. And internal energy, U, let's do it per unit volume. small n times the average energy. Okay, so now let's look at the expression for energy. Energy for a particle of momentum p is square root of p squared c squared plus m squared c4, where m is the rest mass. And you have to take the average of that over this. And the next question to ask is, what is the velocity v that I have to use here? So given a momentum p, I can find the value of v, right? What should be the value of v for a given momentum p? Louder. P by? Why 2m? P by m. Energy is p squared by 2m. Momentum is p by m. That is correct in the non-relativistic regime. We can do that. But if it is relativistic, that is not the case. So what would be a general expression? E is equal to gamma m v. So this is mv over square root of 1 minus v squared by c squared. Let's write it in terms of beta. This is mc beta divided by square root of 1 minus beta squared. Now, I have beta squared by 1 minus beta squared is equal to, let's call this xi. Xi is p by mc. Sorry, xi squared. This is the square it. Xi is p by mc, beta squared by 1 was beta squared xi squared. So hence, you'll have beta as xi by square root of 1 plus xi squared. Right? So this is what you have to take into the integral to integrate. Two limits, we can see that if p is much smaller than mc, the xi is very much smaller than 1, then beta is just xi, which is p by, xi is p by mc, beta is v by c, so therefore v is p by m, just as we say. On the other hand, if p by mc is much larger than 1, then I can ignore 1 over here, the beta just becomes 1. So v goes to c. So in those two limits, it is immediately obvious to see what the pressure is going to be. So in the non-relativistic limit, where v is p by m, when you take an average, it is going to be proportional to the upper limit, so it's pf by m. So pressure will be proportional to n times, this is p by m, this is p squared, so p squared by m. So this is proportional to p is n to the power of 1/3. This is proportional to n to the power of 5 times. On the other hand, in relativistic case, you will have p proportional to, this has just become c now. N times c times p proportional to just n times p, so this is 10 to the power of 4. The equation of state, pressure as a function of density, will soften as you go to higher number densities. We're not done yet though. This is number density. You have to connect it to mass density. Because remember, pressure as a function of mass density is what we consider to be the equation of state. Because eventually that is what I have to enter here to solve the equation. So how am I going to connect number density n to mass density? Let's consider the electron case. Number density is any. What will be the mass density in the gas? That corresponds to electron number density Ne. Do electron provide most of the mass in the gas? Consider a star where pressure is primarily due to electron degeneracy, let us say. Okay, so mass density is any times Ma. What is Ma? Okay. No. So let's consider it's a gas where you really don't have bound nuclei anymore, but you can have a mixture of protons, neutrons, and electrons. But nonetheless, what you have said is exactly right. So what you have to do is you have to count the number of atomic mass units per electron. We call that μe. So if it is hydrogen, μe is 1. If it is helium, μe is 2. If it is carbon, μe is 2. If it is all higher elements, μe is roughly equal to 2. So Ne times μe times Mp is your rho. Right? So since this is proportional to Ne, the pressure is proportional to rho to the power of 5/3 over here, rho to the power of 4/3 over there. Instead, if I had neutrons, what do I have to do? Now let's say I don't even have any other species, it's only neutrons. So now number density is Nn, let us say. Okay, so you say that, and which mass is that? The rest mass. But neutrons are moving nearly relativistically. So rest mass is no longer relevant. Okay? In this case, the particles which are providing mass, like the neutrons and protons, were not relativistic. Electrons were relativistic because electrons have much smaller mass. But the mass providers were non-relativistic. So then I can write it like this. In case of neutrons, when neutrons go relativistic, I can't use neutron rest mass and multiply by number density of neutron to get the mass density. For that, we have to find this quantity U. Mass density will be U by c squared. Okay. So this is a critical difference between electron degenerate gas and neutron degenerate gas. So here, if we plot log P over log rho for an electron degenerate gas, I have slope of 5/3 going to slope of 4/3. In case of neutrons, what is going to be the slope at very high density? Rho is u by c squared. Pressure is related to u, right? So at very high density, pressure is going to be proportional to this. So pressure is going to be just some factor times rho c squared. So this slope is going to become 1. And at lower density, it is going to drop and become steeper. So in order to get this expression, of course, you take this V and then substitute this, take epsilon, substitute this, and you will get the full expression. Let me write it down. Okay. This is true for either case. Pressure is m to the power of 4, c to the power of 5, divided by 8 pi squared, h cross cubed, x times 2/3 x squared minus 1 times square root of 1 plus x squared plus sine hyperbolic inverse of x, where x is EF over MC. And U is okay. This is true for both electron and neutron case, except in neutron case, you have to write rho as u by c squared. In electron case, the electron's internal energy is also given by this. But the mass density does not come from electrons. So therefore, you write mass density as n mmp. Yeah. Mm-hmm. Oh, very good, very good. We will come to that. That is one central part of our discussion, which is going to happen shortly. Okay. All right. So now, Here is a gas which has a certain density, which has a certain pressure, right? Now, we are talking about thermal pressure, we are talking about the gravitational pressure required, but this is always lurking because electrons are present, gas is ionized, so at high enough density, electrons will always become degenerate. So let us draw this degeneracy pressure on this. That's my degeneracy pressure line. And I have drawn the ignition temperature of hydrogen over here. In stellar fusion, different stages are actually distinct in terms of temperature thresholds. And that is because the temperature sensitivity of any reaction is extremely high. As you know, the fusion happens because of tunneling. You have a Coulomb potential which is actually very high. And you have electrons with thermal energy quite a bit below the energy barrier. So it's mainly due to tunneling that these two nuclei come together. The nuclear thermal energy is much less than the Coulomb barrier. So it tunnels through the Coulomb barrier to combine. And that process is extremely temperature sensitive. So even if temperature changes slightly, the reaction rate will go up by enormous amount. So therefore, before the next burning stage can arise, the previous burning stage gets completely finished. So the helium burning, let us say, is going to be represented by a line like that. And I can draw other lines. And so forth. Now what you will notice is that, let's take this star. It undergoes hydrogen burning, then contracts, undergoes helium burning, but before it can cross the carbon burning line, it is already being provided support by degeneracy pressure. So the core becomes degenerate. It cannot contract any further. It cannot get any hotter to burn carbon. But if you have a more massive star, then it can cross this, and then be supported. And the higher the mass, the more stages of nuclear burning will go through. And above a certain mass, this actually does not provide any extent of support because at high density, the slope here is the same as the slope of that. So if you go above that, you don't get any further support. And in fact, that effect is also what gives us the Chandrasekhar mass limit. If you take a purely degeneracy pressure supported configuration, then you have different masses which can be held by the degeneracy pressure up to this mass. If the mass happens to be higher than that, then there is no support possible. The Chandrasekhar limit is exactly due to this fact that the slope becomes 4/3 at high density. So that mass for mu equal to 2 is about 1.4 times the mass of the Sun. So here, as you can see, that the degeneracy therefore decides how far the nuclear burning can proceed. If you go down to lower masses, you will find there will be stars which will come and hit the degeneracy pressure even before hydrogen burning can occur. So all stars below this mass, all configurations below this mass come and be held by degeneracy pressure. They will not be able to cross the hydrogen burning line. So these are going to be brown dwarfs. And you go further down, I have not included here the Coulomb interactions. So if you go to less than 1/100th of the mass of the Sun, then Coulomb interactions between particles will become important as well to the total pressure. And then you will have planets. So start with planetary configurations, which are the smallest ones, then go, transit to brown dwarfs, and then to stars. Yeah. Correct. Correct. No, so degeneracy takes precedence when the Fermi temperature is significantly higher than the local temperature, right? And that is always going to happen. If you go to high enough density, so Fermi temperature is Fermi energy, so that's energy corresponding to this. So let me also write down what is the Fermi energy. Epsilon F is so as you go to higher and higher density, Fermi energy is going to go up, and the Fermi temperature Tf is epsilon F by kT. Sorry, epsilon F by k. If that is larger than the local temperature, then degeneracy will become prominent. In principle, you can derive all of these for finite temperature as well. So they will have correction terms, but it's not important for this discussion. When you do actual stellar configuration, you have to take all of that into account. The thermal corrections have to be taken into account too. But it's the thermal part of the energy which will eventually get radiated away. And if you leave the configuration by itself, ultimately it will settle down to a zero temperature configuration. Okay. So now we have looked at how a star proceeds via different stages of nuclear burning to a stage where you have the core, of course, the whole star is not consuming nuclear fuel. And that's because the whole star is not at the same temperature. All this discussion we have done so far is for the central temperature. But for the sun, the central temperature is 10 million degrees, the surface temperature is 6,000 degrees. So there is a big drop in temperature starting from the center to the surface. Typically, about 10% of the mass of a star is involved in the nuclear burning. So eventually, when you're looking at the processed core, it will have something of the order of 10% of the star at a given point of time. So now let's see what happens when you have a star which has a core which has finished burning hydrogen. Now there is no energy production over there. As we discussed, this central portion is now going to contract. As it contracts, its temperature is going to go up. If it goes up high enough, it may start burning helium at some point. But before that happens, it's going to contract and it's going to produce a little higher temperature, and that higher temperature is going to cause hydrogen which was surrounding it, which had not burnt, now become hot enough to burn. So you will now get a source of nuclear fusion which surrounds the central core, produces a lot of energy, and this energy is going to heat up both the core and also provide thermal balance to the outer layers of the star. One thing that happens is that the luminosity goes up and the outer layer is driven out, so the outer layer becomes more dilute. The star becomes a giant, goes to the red giant phase, and the core slowly contracts, but most of the energy is going to come out of the shell burning, hydrogen shell burning. As far as the whole star is concerned, this is like the central burning. It's just that it's a matter of detail that the core itself is not burning, but something's burning around it. Now, how big a core can be thermally supported under such conditions? That plays a key role in what happens next. So let's consider the radius of the core. Let's call it RC. Okay, it's a core radius RC, and we will use the stellar virial theorem to look at the property of the core. So we have 4 pi RC cubed, P at RC, let's call this PC, is equal to, I'll put gamma is 5/3, so therefore I'll put 2U is EG So this is equal to minus G mc squared over RC, some constant C1, another constant C2 times U is proportional to mass of the core times the temperature of the core. So that means PC is some C2 times mct over RC cubed minus C1 mc squared over RC to the power of 4. Let's call this alpha 1, alpha 2, so that these C1 and C2 are different. Okay, so there is a relation of this kind. So if we then look at how it depends on RC, you will notice that it has a peak. At small r, this dominates, it goes down. At large r, of course, the whole thing goes down, but at a different rate. So it has a maximum PC max as a function of RC, which you can derive by differentiating this. Now this is holding up the rest of the star. So therefore, at the base of this envelope, the envelope has practically the full mass of the star. So the base of this envelope, PE must be equal to PC and TE must be equal to TC. Both mechanical and thermal equilibrium. And that I can get from, I've written somewhere, T to the power of 4 over m squared. So PE is some C3 TE to the power of 4 over m squared. So PC max, so okay, so that will have some value like that. TE, TC, and so on, they are hydrogen burning temperature. So that is practically fixed. For different values of RC, PC will be different. And let's say I have an envelope for which PE is given by this. This, as you can see, is not dependent on RC. Then I have two possible solutions here and there. And you will notice that this is actually an unstable solution. This is a stable solution. Unstable solution means that if you compress this slightly, that means you make RC smaller. Then the pressure of the core goes down, so therefore the whole thing will get more compressed. If you expand the core, make RC larger, pressure of the core goes up, so it will tend to further expand. So this is not a stable solution, but this is a stable solution, where if you reduce RC, pressure goes up, and it will expand back. Expand RC, pressure goes down, so it will contract back. So this is a possible solution. As you can see, this is a function of m, this is a function of mc. Now, for different values of mc, this whole curve will go up and down. And at a certain value of mc, it will be such that PC max is equal to PE. The larger the value of mc, the lower this is going to go. So there is a maximum value of mc for a given value of m, for which support is still possible. Otherwise, the support disappears. So now this shell, which is burning, is going to produce more and more ash and going to add to the mass of the core. So you may start in a configuration like this, and as more and more mass is added to the core, this curve is going to go down. And at some point, it is going to go below this, and then there is no thermal support possible for the core. The core is going to just collapse rapidly. It will stop collapsing only when it gets fully degeneracy pressure supported, if degeneracy pressure support is still available, which means as long as the total mass is below the maximum mass that can be supported by degeneracy pressure. The solution of this comes out to be mc max over m is roughly equal to 0.37 mu envelope by mu core squared. So mu core is roughly twice mu envelope because this is a process material. Half squared is 1/4, so it's about 10%. So if the core mass exceeds about 10% of the total mass of the star, then the core is going to undergo uncontrolled collapse. But if it is less than that, then it can still be thermally supported while it is not generating its own thermal energy. And since this is a fraction of the total mass, the size of the core that it can grow in this process is larger for larger mass stars. So if you start with a very heavy star, then you will generate a thermally supported core which is larger than the Chandrasekhar mass. So then, when the thermal support is no longer possible, it will collapse all the way down to a more compact object like a neutron star. And we'll start from this in the next lecture.
Any more questions? Okay, so let's thank Dipankar for this excellent lecture. We'll continue.
Thank you. So we meet tomorrow at the same time.